In this video, we're going to look at some physics that you're probably already familiar with, something that you've seen before, and that's projectile motion. And you may have seen this in your high school physics classes or in college physics classes. But essentially, projectile motion is kind of a special situation of rectilinear motion, where even though you're moving in two directions, those directions have very distinct boundaries. They have very defined, known variables that are going to happen to them. So with projectile motion, what we're talking about with that is generally we have some object or particle or whatever that is being projected. It's becoming a projectile, right? So some object, it could be you kicking a soccer ball that launches at an angle, comes up, and comes back down to the ground. And it may not always start at the ground. You may start and end in various places. You may not always be going up at this angle, an angle theta. You may be going straight out, for example, or you may be pointing down even. And it could be anything. It could be water coming up out of a spout, anything that is just creating this arc motion that's subjected to gravity. So that's really the key special thing that's happening with projectile motion, is that our acceleration is constant. So once that projectile, leaves the slingshot, or your foot hits the ball, or anything that is happening to it, a biker makes a jump. Once it leaves, there is no more acceleration being added to it. The only thing acting on it is gravity. So these are a special case where you have constant acceleration. So generally you have something that has some initial velocity. It's going to leave at some angle, and then you have these distances x and your height y. We're usually using some kind of xy coordinate system with these projectile motion problems. So with this, for our constant acceleration is always going to be subjected to gravity. So we have that constant acceleration, g. Sometimes you'll see it as a sub c for constant acceleration, but in our projectile motion problems, it's going to be gravity. And our two gravity values that we want to have in the back of our mind are going to be our SI unit gravity values, which is 9.81 meters per second squared. Or if we're working in US units, that's 32.2 feet per second squared. So really, if I look at what's going on with my velocities, because my acceleration is constant there, I still have to look at my velocity. Now, for example, in the x direction, if I look at my ball at any point on this curve, anywhere that this thing is traveling, my Vx is always the same. Velocity in the x direction for projectile motion is always going to be the same as where it left that ball position, right? There's no extra force behind it. There's no extra acceleration. So it's only that initial velocity that it was given, v naught x, is the same as Vx. So this is the other special condition for projectile motion, is that your initial velocity for x is your velocity for x everywhere. We have constant velocity in the x direction. So constant acceleration for our y, no acceleration in our x, and then we have a constant velocity for our x direction. Now this is a little bit different for our y direction. So our y direction, because we're subjected to that gravity always acting downward, right? Our g is going to act downwards, so you'll often see these with negative signs in front of them to represent that our gravity acts downwards. So I have some starting velocity in the y direction, and then this velocity gets smaller and smaller as I approach the apex of my curve here. The maximum height at the inflection point there, maximum height of my curve, my velocity in the y direction is 0. Right, because my velocity is going to be changing directions. First, I have velocity, this particle is going up, 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 and then all of a sudden it's going down, down, down with these negative velocities. Whoops, these are not initial. These are just Vy, 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 Vy. Initial is only the first one over here. All of these should just be regular Vy, where Vy gets smaller and smaller till it hits 0 at the top, and then Vy gets larger and larger in the negative direction. Right, so our Vy we have to be cognizant of is not constant, it is changing. It's subjected to a constant acceleration. But our Vx is a constant velocity. So what that looks like is essentially a set of two different rectilinear motions. Right, we're looking at y direction rectilinear motion and x direction rectilinear motion. It's going straight line x, straight line y, and then they're pretty much just combined together to give us that arc. So our equations that we're used to seeing are the kinematic equations, and these are the ones that you've probably seen in physics before. These are our common kinematic equations, where if I look at my x direction, my x, I have just the constant velocity. So if I look at those, A is dv dt, all of those types of equations, there's 0 acceleration, I integrate, I have a constant velocity, and then I'm going to have an x value as a function of time with velocity if I were to integrate that. But I'll spare you the derivations of all of these, and we'll just look at the equations here. So for my x, I'm going to have x is x naught, our initial position, plus v naught x times t. So that's our x component of the initial velocity times the time it takes to go through that loop, wherever we're looking at on our curve. And then we have our y equations, right? So there's only one equation for any x values. X is x naught plus v naught x times t. But we also have y values. So we have Vy equals v naught y. So our velocity in the y direction is the initial velocity in the y direction plus ACT. And you may also see this written as Vy is v naught y minus gt. Sometimes people will skip the step of having to put in a constant acceleration, since we're usually assuming that we're on Earth, subject to these constant gravities. So you might see it either way. It's just important to note that our gravity is going to act down, so this will become a minus sign whether you have it within g itself or whether you write out the equation with a minus sign. So that's another way you might see it. We also have Vy squared equals v naught y squared plus 2ac, again that stands for constant acceleration, y minus y naught. That's our velocity, our y velocity at a given point squared equals the initial y velocity squared plus 2 times acceleration times change in height. That's our y minus y naught is change in height. And then finally, our last y equation, y equals y naught. So that's our position, our y position was our initial y position plus v naught y times t, so our initial velocity in the y direction times t, plus 1/2 a sub c t squared. 1/2 acceleration times time. And so these are our big four. Anytime we're looking at doing something with projectile motion, these are the guys we want to use. Now, these can be derived. We can derive these from our relationships of A is dv dt, v is ds dt, substituting in x's and y's for those s's, for those position locations. And we could get these because we have a constant acceleration. We can do these integrals and we can get these kinematic equations. So even if we don't know these, if we don't have these memorized, we can derive them. We can always find them in a pinch when we need them. I'm always going to give them to you. I'll have them in a formula sheet. But just know that your engineering brain, we can always go back and find where these things come from. We can derive things and figure them out without having to be spoon-fed equations all the time as we were maybe in high school or in lower level courses. But with that, let's go ahead and just take a look at a couple of simple examples, starting with this example. So in this example, we have a track for a racing event was designed so that riders jump off a slope at a 30-degree angle from a height of 1 meter. During a race, it was observed that a rider remained in midair for 1.5 seconds. Determine the speed at which he was traveling off the ramp, the horizontal distance he travels before striking the ground, and the maximum height he attains, at the size of the bike and rider. So when we're given a lot of this word gobbledygook, what we can do is draw ourselves a picture, really try to understand, visualize what is happening in this problem. So a track for a racing event was designed so that riders jump off a slope at a 30-degree angle from a height of 1 meter. Right, so what we have is we've got bike rider. There's a ramp that they're coming off of. Right, so here's our guy. He's coming off of this ramp. Is at a 30-degree angle and has a height of 1 meter. During the race, it was observed a rider remained in midair for 1.5 seconds. So remained in midair means that the time it took to travel this little projectile motion path, t equals 1.5 seconds. Right, and here's the ground. So he's going to start from the top of the ramp and then he's going to end up on the ground. We want to find the speed at which he was traveling off the ramp, the horizontal distance he travels before striking the ground, and the maximum height he attains. So what do those look like in variable terms? Right, the speed at which he's traveling off the ramp, that's going to be our initial velocity. Right, so we want to find, put these over here, we're going to find initial velocity. We want to find horizontal distance he travels before striking the ground. So this is the horizontal distance he travels before striking the ground. This distance, you can call it something like d, but really it's going to be our distance x. So if we consider his start position as the 0, right, ground, and then his starting position 0, you can think of it as x, or you can think of it as x minus initial x if you had some other datum to work with. But this range really is just a distance in your x direction. I'm going to call it x. I'm just going to call it x for now. And then we also want to know the maximum height he attains. So the maximum height he attains, highest portion here, we're going to call that y. So we want to find the maximum height, we want to find the distance, and we want to find the initial velocity, given that we have a time. And a time is kind of the only thing we have that's outside of this diagram that we don't see here. So you can start with any one of these. One may be easier than another, but it really just depends on which one of these handy dandy equations that I have over here to the side, all of these projectile motion equations, which one you want to use. Because usually you can find any of these in any order. Maybe you solve for a variable and then you plug it into another equation. So if you can figure out what's the best equation to use when, you can save yourself a little bit of calculations. But if not, you can always plug things into other things and solve in a longer form way. So if we want to find our initial velocity, do any of these four equations jump out at you as something we could use to find that initial velocity? I'll say for me, the one that kind of jumps out to me is one that has an initial velocity in it, one that has a time in it because time is a known variable for us. Acceleration is a known variable for us. And we also know the start and end heights during that full time of travel. So really, to me, this second equation here looks like it's going to be my best bet to find that initial velocity. So if I go ahead and start plugging numbers into this second equation that we have underlined up there, my y value at the very end, not the height, y value at the end is what I'm looking at because I want to capture the total time, is 0, right? It's the ground. My initial height is the height when I'm leaving the ramp there, when I start entering the projectile phase, is 1 meter. Plus v naught y, we don't know, this is something that we're solving for, times t, 1.5, plus 1/2 times acceleration. Remember to make your acceleration negative. Right, we're working in meters and seconds here, so we're going to use our 9.8 value for our gravity, negative 9.81, times time squared, 1.5 squared. Now it's just a matter of plugging this into a calculator to get our initial velocity in the y direction. I get, from my calculator, 6.7 meters per second. If I think about the velocity that I have up here, this initial velocity, I have a y component, and I want to think about how I can get this actual overall initial velocity. So I can relate this y component to the overall velocity using that triangle. Right? So I have this velocity here. I can make that triangle just like I have in the ramp where this is 30 degrees. V naught y is this leg of my triangle, opposite leg of my triangle, and then V naught x is going to be the adjacent side of my triangle. So I can use this trigonometric relationship to find out what our V naught is. So our overall V naught is going to be, let me write this. Right, our relationship between V naught y and V naught is sine, right? Because sine 30 gives us opposite over hypotenuse, V naught y over V naught. Which means if I want to solve for V naught, I can take my V naught y value, which is 6.7, divide by sine 30, and I get an initial velocity value of 13.4, call it 13.4 meters per second. Perfect. That's one down. Now I just have 2 more to go. So with that known, I can go ahead and start looking for this x value. Because if I look at my x equation, looking at my x equation now and this triangle relationship, I can find what v naught x is. I know my t for the whole thing, and that will give me my range. Only equation I have to do with x's, so it's really the only way to find your x value. It's the only way to find your distance. So x minus x naught, that's our total distance traveled, is going to be v naught x. We said this is going to be v naught cosine 30 is v naught x. That's going to give me, I don't know if I typed that into my calculator. I don't think I did. I think I just left it as 13.4 cosine 30. That's v naught x times time. So the total time it takes, so that way we're capturing that total x distance. Plug that into a calculator, and I get that my distance is going to be 17.4 meters for my total distance traveled. And not distance traveled like the arc, I mean just distance traveled from in the x direction. So the distance he traveled in the x direction from the ramp to the ground was 17.4 meters. And then that leaves us with our last one here. Then yellow, y. We want to find our maximum height that he attains. So remember that at maximum height we have a special condition here where our y velocity is 0. And we also know our x velocity because x velocity is constant for something in projectile motion. 17 point, whoop, that's a distance, sorry, that's not the right number. What was it? Where was our, write it down here. Oh, I didn't. Well, we know what it is. It's 13.4 cosine 30. Oops, I didn't write that down. 13.4 cosine 30. Pretend that's a number. More importantly, we know that Vy is 0 when we want to go and calculate this velocity to get our maximum height. So looking again at all of our handy-dandy equations on the left side, is there one that's more useful than the others to get us our height? Now, I mean, truly, you could do this with a lot of different equations. You could do this in several different ways if you want to. I'm going to use this third equation. We haven't used this guy yet. I know what my end velocity is. I know what my initial velocity is. I know my gravity acceleration. What I don't know is this change in y, and that's what we're interested in finding. Right? So I just look through my equations, see what I can pick out, see what I know and what I don't know, and if any of them will let me solve for something. So I'm going to take that third equation that we have up there, Vy squared. Again, we said Vy at the crest of that arc is 0. You can square it, it's still 0. Equals initial velocity in the y direction. And where do we have that? Here he is. 6.7 squared plus 2 times a is negative 9.81, times y we don't know. That's what we're trying to find out. We're trying to find out that y value, that height. But we do have an initial height. Why not? We have an initial height. It's this 1 meter value. This 1 meter value. That has to go in here. Otherwise, we're only calculating the distance that he went up. And so this is not what we're interested in. We're interested in the total height from the ground, not just the distance that he went up above the ramp. And so we can punch that into a calculator, and we get 3.28 meters. It's the highest from the ground that the bike goes. So this pretty much encapsulates a basic projectile motion problem. Usually there are several things you can solve for, sometimes that are dependent on other things, and you may have to mix and match that set of 4 equations in order to find what we're looking for. But let's go ahead and take a look at one last example. Have you ever seen the movie Furious 7? It's one of the Fast and the Furious movies that they've made way too many of now, but in it, the characters Dom and Brian jump a car from one tower in Abu Dhabi to another. And actually, I'm just going to play you the clip so you can see and understand what we're talking about.
Dom, cars don't fly! Cars don't fly! Oh, shit!
So what we're going to do is we're going to do some calculations of this jump, of this projectile motion problem, and kind of talk about it and see what's going on in this jump from one building to another. So we have them jumping this car. The car that they're driving is a Lykan Hypersport from one Ithad tower to another. If the car is traveling at its top speed, how far would the car have fallen and how long would it take for the car to jump the gap? So this car coming out of this building, let's pretend like it didn't get bazookaed like it did in that clip. That car is acting like a projectile, right? As soon as it leaves the building, there's no other forces acting on it. There's no traction for the tires to gain any more speed, even if they were pushing down on the pedal full throttle. Nothing, there's no traction, there's no way for it to accelerate anymore. So as soon as it leaves that tower, it's acting like a projectile motion problem. So let's kind of draw a picture. I know we saw it in the video, but let's kind of draw a picture of what's happening with this car. So we have one building that our car is being propulsed out of. Our car is coming straight out from the building. It's on a level floor. So it's going to come straight out with an initial velocity and then fall due to gravity until it crashes into the other building. Right? So we want to know if the car was traveling at its top speed, how far would the car have fallen and how long would it take? So we're looking for time, how long it takes, and how far the car falls in that time period. Why? But notice there's also some secret not given information in this problem, right? It says if the car was traveling at its top speed. If the car is traveling at its top speed, it doesn't tell us what that top speed is, but we're smart people. We can figure it out. We can think to Google what the Lykan Hypersport's top speed is, right? We can say, oh, how long would it take to jump the gap? Well, how wide is that gap? What is the distance between these towers? Right? And these are things that we can Google. These are things that we can find out. As engineers, when we're solving problems in the real world problems aren't often given in these nice little prompts where all of the information is in one little paragraph or one little sentence. Instead, we usually have to seek out information from multiple sources to get all of our ingredients to actually solve the problem. Now, of course, in this class, we're still learning, and I'm going to let you know anytime that we're doing this. Anytime that, you're not given all the information, I'm going to tell you. I'm going to let you know. But just like this, we don't know the top speed, we don't know the gap jump, we can Google both of those things. Right? So when we do that, when we Google what's the top speed of a Lykan Hypersport, I think you get 395 kilometers per hour. So this is the initial velocity we're working with. And then that distance between the gaps, if I Google the distance between towers, distance between those Ithad towers, which are real towers in Abu Dhabi, they're about 50 meters apart. There's not like an exact measurement out there on Google, but this is an approximation based on Google Maps. So again, I'm going to tell you anytime that you're not given information that you need, but just know that sometimes we'll do this as a practice because that's what we have to do in the real world. We're going to have to find information, and we're going to have to not be afraid when we don't know everything to go and find that information. So now we have all of our ingredients that we need to actually do the problem, right? And I'm gonna go ahead, and the first thing I'm gonna do is actually just convert this velocity we're given into something a little bit more usable, because we don't know exactly how long that car is falling in that clip with that bullet time, but I have a feeling it's more like seconds and not more like hours. So I'm gonna convert this into meters per second, something we're used to seeing a little bit more. And so I've got 395 kilometers per hour. And there, in 1 hour, there are 3,600 seconds. And then there are 1,000 meters in a kilometer. When I do this conversion, I get a velocity of 109.7 meters per second. So this is the initial velocity we're working with. It's acting only in the x direction as it comes out of this building, and then we'll gain some y speed because of the acceleration due to gravity. So, thinking about the 4 equations that we have, and I don't have them up here for reference, but if we have those 4 equations that we're thinking about, we have 2 things we're solving for. We're solving for time, and we're solving for y, how far down it falls. Looking at those equations, the best one that we may start with is just our x equation. X is x naught plus v naught x times t. Because we know x minus x naught, we know the distance traveled here, right? We know the width of that gap, x minus x naught, is 50. You know, the range that this goes across. You can say 50 is initial velocity, 109.7 times t. Divide that out to get my time is 0.456 seconds. Wow, they sure spent a lot of time in bullet time for that movie, or something that took less than half a second. So that was easy enough, pretty straightforward to just plug and chug finding that time. And now that we have that time, we can find that y range pretty easily with really any of those equations that we see fit, right? Any of those other 3 equations that can work for us. So the one I would recommend is one that does not have final velocity, right? We know initial y velocity. Initial y velocity is going to be 0, but we don't know what Vy is when it strikes this other building. So we do have an equation that's going to work for us for that. I'll move all of this, I think. I might just delete it. I'm going to put in my other equation. So my equation that has no final velocity, whoops, y minus y naught equals v naught y times t plus 1/2 at squared. I know my time. I know my initial velocity. It's 0. I don't know this change in y. I don't know change in y. This is what I'm trying to find. This y minus y naught equals 1/2 at squared. 1/2 times negative 9.81 times time squared, 0.456 squared. So the y that I get, that change in y, is negative 1.02 meters. Right, so negative just telling us that it's going down, it's falling downwards. It goes down by about 1 meter. So the car would fall about 1 meter. So that's not very much. I mean, a meter, that's about 3 feet. Really, the car would probably be crashing into the floor of the building, of the one next to it. It would be basically on the same level, within the same story, the same floor, from one elevator to another. It's hardly going down at all. But I guess a better question is this very realistic? Is this something that's realistic for the car to even be leaving the tower at the top speed? Right? And the answer is probably not. Right? I mean, the amount of time and the distance you would need to cover in order to work up from this car going from 0 to 395 kilometers per hour, that is probably longer than the tower is. So it may not be realistic that it's taking half a second to jump between towers and it's only falling a meter. So let's take a look at this problem from a little bit different perspective. Let's say we know how far they fall. So what if we say, if the car only falls 2 stories, so it's the same problem setup, but now different variables. Same problem setup where we still have the distance between there is 50 meters. The car is still shooting out of the building. But now we're saying we know delta y. Saying if I know that this car falls by 8 meters, about 2 stories, falls about 2 floors, what's the initial velocity? Right, so not leaving at top speed. Let's see how fast this thing is leaving if it falls 8 meters instead. So I want you to go ahead and try this on your own, see if you can get the initial velocity, and then we'll talk about it. So in this version of the problem, we know that we're looking for initial velocity, and we know that our initial velocity is only in the x direction. Which means really, what we're going to want to use to find our initial velocity, to find what that value actually is, we're going to have to use the x equals x naught plus v naught xt. Because really, this is the guy that we're finding. There's no y component, there's only x component. But we don't have a time, right? So we're going to have to use another equation in order to find a time to substitute into here in order to find this v naught x. So again, you can take any of those 3 equations that we've talked about for the y direction. We're going to want something that has time in it, and we're also going to want something that does not have a final velocity, which really only leaves us with one good option. And that's going to be our y equals y naught plus v naught yt plus 1/2 at squared. I'm going to start popping all the numbers I know into that. My initial height I know is, we'll call that 0. And then I know my final height, my final height, we'll call that, well, we could call that 0 also, and we could call my initial height 8. We know really y minus y naught, it's this negative 8 number. So we can combine these. Y minus y naught is negative 8. I'm going to just put negative 8 out here. Negative 8 equals v naught y times t. V naught y, we just said there's no v naught y. That term is not going to be in here at all. No velocity at the beginning there in the y direction for this problem. Plus 1/2 times a is negative 9.81 times t squared. So this is very solvable. I can just pop this into my calculator and get a time of 1.28 seconds. 1.28 seconds. So there's my time, and I can use this time, plug in back in my equation up here. So my x minus x naught, we already know that range is 50. So 50 equals v naught x times t, 1.28. So my initial velocity in the x direction, which is just my initial velocity, I punch that into a calculator, is 39.1 meters per second. And if I translate that back into kilometers per hour, I'm going to get about 140 kilometers per hour, which is still really high, right? That's still a very high top speed. Not a top speed, a very high speed to be leaving the building at. But it could be in the realm of possibility. It may be a powerful enough car that it was able to get up to 140 kilometers per hour before they made the jump. So this is something that is a little more realistic. That maybe if the car did go down by a couple of floors, like it looks like it did in that shot, this could be a stunt that is plausible in real life.